So here is the warm up. It's the same problem I had you guys do at the end of class the other day. Go ahead. Yeah, no, take your time. Yeah, go ahead. Yeah, that's the other stats teacher. He took my statistical tables, but I have enough extras, but it's kind of funny. You did. So I guess work on this while we figure out what the hell is going on. Uh, you'll need your table, or you can use your calculator for this. Right. See, a lot of students haven't really tried, but Regina, can you tell me what formula you used here? Yep. Capital E. Yep. Alpha over 2. That means the critical value, right? And then give me the rest of it. Okay, that's right. So, and we know this is a T interval problem because what do we not know? Well, we're trying to find that out, but let me give this to you. Let's try to break down some of this information. Okay, so I see this number 40 here. How is that relevant to the problem? That is equal to, Bobby? N. Okay, and we're able to use this formula because what is true about N here? Yes, but what's required for the number of people? To use this formula, the requirements are either blah or blah. N has to be greater than 30 or, which we got here, so you could have a sample size that's too big, is what you're saying? N is greater than 30 because the central limit theorem says that we can treat the distribution as normal if N is greater than 30, right? Because you're doing a sampling distribution, right? As you found in your project, right? Remember you did the dice roll and then you did it after you used the means, right? Becomes normal, more normal, right? The larger N is, right? And we decided, and I don't know who, that 30 makes it normal enough. The other thing is that original distribution is normal, right? Because N is 30 means the distribution has been made more normal. If it's already normal in the first place, rock and roll, baby, right? So, okay, now we can figure out why we're using T naught. So let's go through some of these other pieces of information. This 12, is that an important number? No. Okay, now their mean weight loss, 2.1. What is that? Yes, so what kind of mean? It's the sample mean. If we had the population mean, we wouldn't need a 90% confidence interval. And what's this 4.8 equal to? And what kind of standard deviation? It is the sample standard deviation. If we use the T interval and not the Z interval when we do not know the, what about the population? That's absolutely correct. Underline that in your head, right? And that's the case most of the time, because why the hell would you know that? Say again? Because we do not know the population standard deviation. Typically you don't, because you're making a confidence interval for the mean, right? If somehow you know this population standard deviation, Like that would be pretty magical, right? How would you know that if you don't know the mean of the population, right? The whole point is we're making a confidence interval for the mean, right? All right, what's the other piece of information that you got out of this problem? One thing before is written in there. Confidence interval is 90%. All right. So confidence interval is 90%. Means that we have this distribution. We want to find out what's the 90%, right, interval here, right? Okay, so now tell me the degrees of freedom. All right, so our degrees of freedom here is 39, and we want 90% of our area to be in the middle. So, right, right, we have a z table, but you use the t table today because of our situation, right? Because we do not, again, we use t, everybody, when we yes, very important, right? So now we're looking at this table, degrees of freedom, 39. Now, Bobby, how do I decide which one of these values is the correct critical value?
There was the 90, so it has to be down. So it has to be 5 on each side, right?
Yeah, so area in one tail is 5. Area in two tails is 10. So it's this one. That's our critical value. And then from there, it's just plugging everything in. You need to know these formulas. You need to know when to use them. You do this, you're going to get, what did I get? Roughly 1.27. Okay, so that's the margin of error. So then to find the confidence interval, the margin of error is the error from the mean, right? The sample mean. So you do x minus, so we can say this, right? And what numbers did you get when you did that, you know? That's roughly accurate. Okay. So that means, right? This is pounds, right? That means at a 90% confidence level, we are 90% confident that the mean person who goes on the Atkins diet will lose. And again, this is assuming that our sample was simple random, between 0.8 pounds and 3.4 pounds. So does it appear to be effective? So a program would cost, well, it depends your idea, right? So are we fairly certain that people who are on this diet actually lose weight? We are, because these are positive, right? If one of these numbers went into negative, right, or had 0 in the interval, we know that some people, like there's a 90% chance that somebody on that interval would be in the gaining weight. Now, the other thing is it appear to be practical? Is the amount of weight loss, is the mean weight loss significant? Practically significant, ladies and gentlemen. Well, it's demanding. Would you go on a weight loss program if they said, if you go on this program, you could lose, we're 90% confident you're going to lose less than 1 pound and between less than 1 and less than 4 pounds. So it's not practically significant, right? it causes a weight loss, but not enough that it's worth to go on this program, right? So do we see that the answer to this first question is, does it appear to be effective? Well, yes, it does appear that people lose weight, right? So statistically, it's a significant weight loss, right? But is it practically significant? No, right? Remember, we did this before. We had a test that we were able to show at a statistically significant level, right? It increased your chance of having a girl from 50% to 51%. Remember this? Way a long time ago. That's statistically significant, right? Because we showed we were like 99.9% confident in that case. But the difference, right, is not significant. Okay, so here we found a confidence interval for a population mean, right? Now, we also found a confidence interval for what parameter before this? Population mean, and before that was what about a population? This one we used the Z intervals instead of a T interval. You should sound familiar, right? We did a whole section on this. We spent a whole day on it. I'll just wait to hear. You've been assigned homework on this. It's worrying me, guys, who can't seem to remember what we do from day to day, even though that you were able to do it on the assignment. I'm just going to wait, all right? What was the other? We just created a confidence interval for a population mean here. What else did we learn how to create a confidence interval for? This is 7.2. 7.1 taught us how to find the confidence interval for what parameter? Sample is not a parameter. We spent 2 hours learning this last Monday. The Z-score is not something we estimate.
Proportions?
Yes, the proportion, the population proportion. We spent a whole 2 hours learning how to do that. Does that sound at all familiar? Okay, so, right, we did the same thing, except we did use a Z-table to do it, right? So we used P hat to estimate P, okay? What are some other things? What's another parameter we might try to estimate? That's what today's lesson is about. Hint, it is a population parameter that is not known here. Not known, and we spent some time already today talking about how it is not known. Correct. We will be estimating a population standard deviation, or what's the square of the standard deviation called? Yeah. So that is what this next section is about, estimating, right? Try to keep some unity of the topics, right? If you look at the textbook, right, you will remember these things. Or just check what we did a while ago. I usually ask something about what we did before. So again, I guess our learning objectives: explain a confidence interval, calculate the confidence interval for a variance, and calculate the confidence interval for a standard deviation. It's pretty straightforward. If you have it for the variance, you can just take it, right? You are going to use the chi-squared distribution, right? And this is spelled CHI, but it's pronounced chi. This is a Greek letter, all right? Can you guess where that is? Where someone might find that distribution? You've had it with you this whole time. Yeah, which page?
On the third, fourth page.
Table A4. Chi-squared distribution, correct. Right, let me just backtrack a bit to remind you how to do something. We can do what we just did on your calculator. On the stat menu. Go to tests. And go down to t-interval. You just input our data, so this is me doing that, right? So you go from data to stats, because you don't have, data would be like, I want to get an interval based on this raw data, right? We don't have raw data, we have statistics from that data, right? Information about the sample. So you just put in the information, you put the confidence level as a decimal, you hit calculate, boom, there's your interval. Okay. All right, so who can guess, right? So in this thing, what do we use, in our example we just did, what do we use as our point estimator for the mean? For the population, we use the point estimator. A point estimator is what? It's just your best guess, right? And then we use that. So we used what as our population estimator? Should we estimate our population mean? We used our sample mean, right? So what do you think will be our point estimator for population variance? All the same pattern. Yeah. Pretty straightforward, right? So how do you estimate? That's population variance, right? Sample variance is the best point estimate of population variance, right? Now, when constructing an estimate of a population standard deviation, we have to use something called the chi-squared distribution. So chi-squared shows us how our, right? We showed this before, right? So if you remember, right? We had a symmetric, the z distribution and the t distribution were both symmetric, right? Because the sampling the sampling distributions of your mean and your proportions will both be symmetric. Now, do you remember, was that from last chapter, was that true about the variance? What? It was not a bias estimate. Well, standard deviation is, right? Not variance, which is weird to me considering that they're related to each other. But if you remember the picture, it was not. It was a skewed distribution. And it was skewed right. So the chi-squared distribution, since it's supposed to help us estimate the distribution of sample variances is also skewed right, unlike the t and the z distribution. Notice it also has the origin. Your t-score or your z-score can be negative. You will never have a negative number for a chi-squared thing because it is mathematically impossible for your variance or your standard deviation to be negative. Because if you remember from the formula, it involved squaring, right? That procedure that you use to find the standard deviation, aka the variance, involved squaring numbers. And when you square, you get a positive quantity. So that's kind of one way to think about it, right? You have some number, it can't really be symmetric because that would require the possibility of having a negative variance, which is mathematically impossible. Now, chi-squares also involve degrees of freedom. Do you remember what happened to the t distribution? As you had more degrees of freedom, it became more and more like what distribution? Say again? Normal. Same thing with the chi-squared distribution. But you might be wondering, the normal distribution has what property that the chi-squared distribution does not have? Normal distribution is the bell curve. What's the most remarkable? What's the feature of it? It's symmetry. This one is not, right? So this peak moves to the right as the number of degrees of freedom increase. Right? So another thing that I just said, chi-squared, never negative. So look at this, right? Degrees of freedom, 10. It is very skewed, 20, skewed, but starting to look, it's less skewed. Would we agree with that? It's starting to look like, so if you had infinite number of degrees of freedom, it would be the same as the normal distribution, just with t. Remember t, the peak didn't move, but the tails became thinner, right? Does that sound familiar? Okay. So the other thing is the distribution is not symmetric. That comes up, makes one other thing more complicated. So when we found our error, what did we do in the warm-up? So we found the error, right? And then we found the confidence interval by doing what with the error? You can actually see me doing it right here. I did what with the error to get the confidence interval? And that works because the mean, right, inside of our confidence interval, the mean, the sample mean, the point estimator should be in the dead center because what type of distribution is this? It is not normal because it's the t distribution, right? That's why you use the t-table correctly. But what feature allows you to just go to the left to the same and the right the same? Right, the bell shape is what property is important of the bell shape? It's symmetrical, right? Do you think we can do something similar for the variance? Well, not, because the variance is just, it's skewed, right? So, right here we can say, all right, hopefully that gives you some intuition. Here's where we said, right? We said this is our middle, right? Let's go E over here to get 45%. Then let's go E over here to get 45%. That method, ladies and gentlemen, will not work It's skewed, right? We're going to end up, if you did that, right? Notice I roughly did it. These areas are not the same. So there's no, that doesn't work. So that's the main complication here. You cannot do this. There is no margin of error, because margin of error implies to the left, to the right. So you need a completely different method. And you'll see, right, before when we looked at the like, Bob, you helped us locate the critical value. How many critical value, right, on the previous, how many critical value, I'm not asking you what it is, you don't need to look at the table. How many critical values did we find? One. And we didn't need the other one because the other one's just negative that, right? Which is why when we found the margin of error, the other critical value for the negative t, we would have just subtracted, right? So since this is skewed, not symmetric, how many critical values do we think we'll always have to find? 2, because again, everybody, what's the important property here? It is not, it's skewed. So you're going to have 2 different critical values. It's okay, right? Because I'm not telling you this, right? I'm trying to help you think about it. So this is your table, and it kind of shows you here, right? So it tells you, right, before it was always finding area to the left. Now all of a sudden, by convention, we're finding to the area to the right of the critical value. Why? I don't know. But let's say correct. It can't be skewed to the left because you can't go negative. That's not exactly, there's more like deep math, but like intuitively, right? Let's say that, you know, let's think about it, right? Let's say that your population variance is 2, right? Your population variance is 2. There's a non-zero probability that your sample variance would be 5, right? That's off by 3. There would be a 0 probability that your sample variance would be -1, right? So you can be off more, it's easier to be off to the right than it is to be to the left. So here's how you read this. Degrees of freedom. So this tells you what's this area to the right of your critical value. And these numbers are all positive. So let's say you choose some degree of freedom, let's say 9. So this is saying, right, for this chi-squared distribution, right, if I wanted to find the number that cuts off, let's say I want this to be 95% and this to be 5%. Well, I would have to choose this. Chi-squared would have to be 16.91. Everyone following? It's the same way that we've read these tables before. The only thing that's different is the other, like the Z table, it was always giving you area to the left. Here it gives you area to the right. They have to add up to 100. Why they decide, why that's the convention, I don't really know. Someone decided that who's either smarter than me or maybe they're just dumber. I don't know. I don't know why. So this is kind of the idea of what you need to do. You need to find a different value for your left and for your right. So, for example, what was our confidence interval for our warm-up? 90%. So in that case, %90 was in the center, right? And it was symmetric. Here, if 90% is in the, not necessarily the middle, but like, by middle, I don't mean dead center. I just mean, I don't know, middle, right? Not the end, right? So if I have 90% here and I want it to be the middle 90%, then I have 5% here and 5% here, right? So when I'm looking for this, well, I want 5% to be to the left, so what would be to the right? I said, okay, let me be more clear. So this line right here has 5% to the left. So what would be the area to the right? 95. So I am going to look for what I call my XL value here. And if, so that will give me this. This one right here I call XR because it is my right critical value. And what is the area to the right of this line right here, everybody? Well, 5. Oh, I should have wrote 0.5 here, right, 0.05. But so then I look in this table, this column, for my right value, right? And notice there is no symmetry here at all, right? That's why you have to find two different critical values. So in this case, for 9, XL would equal 0.325, and then XR .961. I know that's confusing, so I'm going to do it again for y'all, okay? All right. So we're going to find XL, or chi squared L and chi squared R, for a particular confidence level and a particular sample size. So the easy thing is I want to translate that sample size to the degrees of freedom, right? So Bobby, the degrees of freedom here will be 21. Okay, so first you want to identify your degrees of freedom. Then we want to identify our confidence level and draw a picture. So what is our confidence level here? So let's draw out a right skewed distribution. I'm not very good at drawing, you can see. All right. So our confidence level is 95%, right? So we want to find, what that means is I want to find the center 95%. So draw out roughly what you think. So before we could do area in one tail or two tails. It was, right, it just depended on how you looked at the table. Here you're always looking at area of one table because each tail, right, before both tails look the same. They're mirror images. Notice that's not the case here, right? This tail right here is narrow and tall, and this one is wide and short, right? That's just what's going to always happen if you have a skewed distribution. Okay. So I have 95% or 0.95 of my, everyone listening, in the middle, right? What then is in each tail? Well, let's think about it. How much area is shaded yellow altogether? Does everyone get 0.05? Because that's what's remaining, right? All right. So what is then in each yellow area? 2. Dividing by half is multiplying by 2, but you mean multiply by 1/2. I know what you meant. Yes, I just wanted to be careful because you type, right? Okay, so.
I get that there's like.
Yes.
Like, this. Wouldn't it be different since it's
Yeah, good. That's a good question, right? So I want 95%. There are different 95%, right? I could start here and have 5% to the right. I could have the whole 5% to the right. I could choose 2 other lines that have 1% to the right and then the other 4% here. So it is skewed right. Yes, it would be different if I went out like a particular distance. But I am saying I am finding the 95% middle area, and then I'm going to split the remaining area on the 2 wings. But the fact that they're skewed means that the shape will be very different of those, okay? So we need to figure out how to do that, right? There could be it's just easier, right? In some bizarre world for the confidence intervals, they could say, well, I want a 95% confidence interval. Let's choose it not to be the middle 95%, but let's choose it to have 2% here, 3% there, right? But that's okay. But then we have to, so this thing right here is called chi-squared L. This one is called chi-squared R, right? And we will use our table to find these values, but we have to remember how to read our table. So, Bobby, it says, and it shows on the bottom on your table, the numbers in the table represent what area? Correct. It is to the right of the critical value, right? That is what our table does. Okay, so we need to do work to find chi-squared L and chi-squared R, correct? Okay, so for chi-squared L, I have 0.025 area to the left, right? But I don't want to look that up in our table because our table, again, as Bobby just said, gives us area to the everybody. So what is the area to the, I need to know the area to the right to use my table. So what is the area to the right of chi-squared L? Well, what's the area to the left, everybody? So what's the area to the right? Well, what does it add up to altogether? Yeah, no, 97.5. There's two ways you can think about this, right? So thank you, Ara. So there's two ways I can think about this. What's the area to the left? Everybody, you just said it. Right? What's the total area? Total area underneath any probability distribution is what? 1, aka 100%, right? So 2.5% to the left, aka 0.025. I shouldn't put an O there, but the remaining, I can subtract, do 1 minus this, right? To get that area to the right, correct? Or I could say, well, to the right of this value is this white portion, which is what percentage? Yeah, 95 as a percent or 0.95, right? And the right tail, which is, yes, and you can add them together and get, yes. So that's the right of the left one, right? The right of the right one is super easy. What's the right of this line? Okay, so that tells us how to use our table. Okay, so n is 22. So what's our number of degrees of freedom, everybody, just before we go there? 21, right? So let's look at the part of our table that's 21 degrees of freedom. And we said the first area to the right for XL was 0.975, and the other one is there's different ways to think about it. This is the way that I think about it, right? So your first number, right, is your total area divided by 2, right? Your tail area, this is tail area, right, divided by 2. This is 1 minus that value. The other way is, now notice, between this percentage and this percentage is 0.95, which was my confidence level. So these are my values. Let me just write them down before I forget, okay? And then I'll answer your question. So you can see, right, these are our two values, right? This is 10.283. That's X. Right? One of them has 95% to the right. The other one has 2.5% to the right. So in between is 95%, which is our confidence interval. Did I answer your question, or do you still have one, Regina?
Is this just how to solve for the chi-square?
Yes, the chi-squared L and chi-squared R. Confidence interval, yes, variance, confidence variance interval. But you have to use this table, and it's significantly more complicated than before, right? And then, yeah, these are the values. Let's take a 5-minute break, but you can also spend time doing this. Let's just choose. All right, Myra, how many degrees of freedom do you want? 12? Bobby, what's your confidence level?
95.
We just did 95. Let's do a different one. Okay, confidence level 90. Take 5 minutes to do this, right? And then you can use the remainder of the 5 minutes to use the restroom, right? So I want you to get, yeah, x square R and x square L. Most of you got it. So Bobby, we're gonna help me walk through this, okay? You didn't quite get it. So I want a 90% confidence level. So that means I want my 90% of my area to be in the middle. Okay, so what is in each wing then? 0.05. Okay. And Bobby, so tell me, what is the chi-squared table? It gives me area to the right of the critical value. So chi-squared R is pretty easy to find, because you chose, what was it, 12? You choose a different highlighter color because yellow is going to kind of blend in. So I want chi-squared R will have what percent to the right? You just told me. You just said it. So chi-squared R, let's look at it. We'll have what percent of the area to the right of chi-squared R? 0.05, okay. And chi-squared L will have what percent of the area to the right? So I'm going to look at the table values for 95 and 5. So just notice your two numbers should add up to 1, right, or 100%, and the one on the right is going to be half of the remainder of the top, right? Half of the area in the wings, right, which you get by. Right, you following everybody? Okay. So that's how you get chi-squared L and chi-squared R. So then the other question that you kind of set, so Regina, is what? What do we do with them? Yeah, right. That's what you're kind of asking, because it's not clear how that gets you, or confidence interval for a variance, right? So first, you have to know that you're in a situation where you're there. So we have some sample, right? And in the sample, I've told you what the sample mean is and the sample standard deviation, right? So you just need the sample standard deviation. So here's what you need to know to be able to even use this formula. This has a requirement that's stricter before, right? So this method only works if the sample is simple random. We've always had that before, right? Like before, and I said the requirements it was bifurcated. It was either n is Or, Bobby, always has to be simple random. That's not that, but there's an or. That's all. Simple random's always true. That's a requirement. The original population, right? The population, and that's why I say original just to emphasize, there is normally distributed, right? Because the central limit theorem says the sampling distribution will become more normally distributed, even if it's not originally, if n is large enough, right? But if n is not large enough, is it going to be normally distributed if it's normally distributed? Yeah, right? So there were two things. Either it's large enough or the original population is normally distributed. Does that sound familiar, Bobby? Okay. For to use the chi-squared distribution, the original population has to be normally distributed. That's it. It has to be normally distributed, and it is a strict requirement. Doesn't matter if the original population is not normally distributed, you can't do this. Doesn't matter how big m is, or sorry, n. We're following here, okay? So that's your requirements, right, to be able to use the formula. That's on the next page. So there's no margin of error, right? Because, again, you can't use the margin of error method because, Regina, it's the original population is, a normal distribution is symmetric. So when the mean is normally distributed, not the standard deviation. And what's the problem with chi-squared is, what's its special feature? It's skewed. So it's not the interval should not be symmetric because the distribution is not symmetric, right? Before, you could just say, all right, my interval is going to be symmetric. What's this distance to the left, to the right? You can't do that here. So that's why we have a different formula for the left bound of the confidence interval and a different formula for the right bound because, again, the distribution is not symmetric. Otherwise, I could just give you a formula, right, for the error, and then you could add that and subtract it from the variance. Here, you cannot. Maybe you know what is strange about this formula? Or at least counterintuitive. There shouldn't be an equal sign because this is a confidence interval, right? I should have one formula for the left bound, one for the right. Yes, but something is counterintuitive just why would that be counterintuitive? That makes sense to me. Our estimate for the standard deviation of the population should be based on the sample standard deviation, right? Same with variance. Something really counterintuitive is here. No, it's got squared in the name, so that to me makes sense. Well, that makes sense. There's supposed to be an upper bound and a lower bound. I would expect that every time. Something here that's really counterintuitive, and I don't know why we're not seeing it. Say that louder. That's the weird part, right? Now, that should make sense if we think about it. Notice you are dividing, right? Does everyone see that? That's weird, but that makes sense when we think about it this way. So Bobby, give me 3 numbers in order that are each like fairly small numbers. Actually, it doesn't really matter. Just give me 3 numbers in order.
3, 2, 5.
That's definitely not in order. 2 is less than 3. is less than 5. But notice 1/2, 1/3, 1/5, which way should my signs be? Is this true? It's inverted, right? So this number is bigger than this one, right? So since we're dividing by it, we have to switch, right? If I want these signs to be in the same order, I can keep the 1/3 in the middle, but I'd have to move the 1/5. Do we see that, right? XR, chi-squared r, is bigger than chi-squared L, so dividing by chi-squared r will give us a smaller value, right? And dividing by, so that is something that's weird. You have to get used to switching them, right? But if you forget to, hopefully you'll notice once you get something that says like 10 is less than 8, which is less than 6, you're like, that doesn't make any sense, right? You can switch it at the end if you make the mistake. We following, ladies and gentlemen? Okay, so that's this formula for the variance. So to take the square root of this, will give you the formula, right? I suggest instead of memorizing both of these formulas, just find the confidence interval for the variance, then take the square root, right? One thing you want to be careful is you don't want it, right? This chi-squared r, right? What a student might accidentally write is, well, I can take the square roots of, right? I only have to leave the square root of n minus 1. S squared square rooted is just s, right? And they might think chi-squared r square rooted is just xr. I guess that's true, but these chi-squareds, notice this table has values that are called chi-squared. They're kind of, I don't want to get too much into this, it's pre-squared. So if you use this second formula I gave, it will give you the wrong answer because these values are pre-squared. You can't have the square root cancel out the square because then you would be looking at completely different values. So just take the square root at the end, and I'll just. So roughly speaking, here's the procedure. Verify the 2 requirements are met, right? And then again, right, Mons mentioned simple random. That's always a requirement for everything we do in this class. What's the second requirement, Bobby? The original population must be. Nope, that no longer works. Yes, the original population, right, whatever it is, human height, right, has to be normally distributed, right? N being greater than 30 is fine for mean and proportion estimations, right? Does not work for standard deviation, right? You have to know that the original distribution is normal. So before, Bobby, it was greater than 30 or normally distributed. Here it's just normally distributed, right? So then you use the method we did before, right, to find x chi-squared r and chi-squared L. You use this formula to find your confidence interval of your variance. You take the square root of that to get the confidence interval of your standard deviation, which is what we mostly use, right? Like, why do we, the variance is kind of a weird measurement. Yes, Regina.
You know how we have the square, even though they're the same formula. Let's say like you solve that formula that's on the board right now.
Mm-hmm.
That how we find it?
Yes, and we will do an example, exactly. And I'm going to suggest you don't because, or I mean, you could do that. That works fine. But normally this is easier because I feel like if you see it inside the square root, you're tempted to cancel out the square root and the square in the denominator, which you can't do because we have a chi-squared distribution. It's the numbers in this table are pre-squared. I don't even know what, if that doesn't mean anything to you, don't worry about it. Just be careful about trying to simplify the formula. So let's do an example. So here's the thing here, right? Now, you might be confused, like, I thought we're using the chi-squared distribution. What does it mean that it's normally distributed, right? So, all right, let's read this, right? So, you may have heard this, right? I don't know if you guys remember. You might be too young. You're probably around like 9. Flint, Michigan, about 10 years ago, they discovered that there was a lot of lead in their water there. If you have childhood exposure to lead, when you are an adult, you will have a lower IQ than if you did not. It's very sad, right? So it will cause lifelong effects if you're exposed to lead as a child. So thank God we don't use lead pipes anymore. We don't use lead gasoline. You think older people who might be my parents' generation, not yours, might be a little crazy. They probably are, because they've been exposed to a lot of leaded gasoline as children. Okay? Thank God we weren't. Right? So, in the group with medium, right, lead exposure, that group has a standard deviation, right, of this number of about roughly 14.3 IQ points. Right? Consider the sample to be simple random, and we know that IQs are normally distributed. So what it means is that the IQ scores are normally, if the IQ scores are normally distributed, right, and I take different samples from that population and look at the sample variances of each of those sample variances will be distributed in the chi-squared distribution. So original measurement being normally distributed results in the chi-squared distribution being true for the variances. Okay, so that's what I mean by that. So let's just take out the pieces of information here, all right? This 22 is equal to what? This number right here it is the sample standard deviation, right? And I wouldn't be giving you the population standard deviation because the whole point is to create a confidence interval. Yeah, so we're going to say, like, I'm 95% confidence the standard, right? Like, it's at least this and at most this, right? So that's all we need. Although the other thing in here is the, yes, interval. So that's 95%. So that means we're going to have something that looks like, that's 95% in the center, which means what percent is in each wings? Okay. And we have every variable we need on this page except for what? What are we missing for this formula here? Okay, sure. It's not in the formula directly, but I guess I guess we have it in the degrees of freedom is going to be 21. What else do we not? Well, I can find it, but I don't have it now. What can I can't just jump in now because I'm missing what? Chi-squared L and chi-squared R, right? Remember, this is chi-squared L. This is chi-squared R, right? Okay. So, Bob, you're going to help me with this because you struggled last time, so I think you get it now. So I have a 95% confidence interval, right? And this is my picture. So I have 95%. That's my center, right? What's an inch wing then? Okay. And Bobby, what does these values in the table? These when it was referring to an area, it is an area to the right. Okay. So for pi squared r, well, first let's remember, I forgot. How many degrees of freedom do we have here? Okay. So here we are. Now, Bobby, for chi-squared r, what is the area to the right? Just look at the picture.
0.
Okay. Now, what about for chi-squared l? Mm-hmm. 0.975. That's correct. And Bob, what do you notice these answers, these two numbers add to? And that's always going to be true. So once you found this, you can subtract that from one to get the other one, right? And also notice, Bobby, we have a 95% confidence interval. Notice the difference between the two numbers that I circled. The difference is 0.95, which is the confidence level. That should always be the case, right? Because I'm finding the middle, right? So then my values are yeah, so 10.283. Oh yeah, I don't know why I circled that one. And so David, what was the weird thing about in this formula about the chi-squareds? They're inverted, which you see, David, the chi-squared r is on the left. The chi-squared l is on the right. Why is that, Regina? So which one's bigger, r or l? So when we divide, which one's going to cause it? So dividing by the bigger value or the smaller value is going to give you the smaller. No, you know that. If I divide by a bigger number, I get a smaller number, right? Yes, if I divide by 100, I'm going to get a smaller number than if I divide by 30 or whatever, right? So the minimum should be the one that I get when I divide by 35. The maximum will be the one when I divide by 10. Does that make sense, everybody, now? So now we just plug in. All right, notice n minus 1, that's the same as the degrees of freedom. 21, right? And then so the formula is this. And notice there's a square there, but the values in our table are pre-squared. So do not square these numbers here. Notice the numerator for these fractions is the same. The only thing that's different is the denominator. I want to show you a trick to save your time on the calculator since both calculations are so similar. So it's 21 times 0.14. I don't know why I gave us so much precision. 29263. That's squared, and then we divide by 35.479. Everyone able to see that? So that is going to be my lower bound, right? Yes. Okay, so that's my first number, right? Now, to save myself some time, right, notice the numerator is going to be this. So I just calculated. This one, and I got whatever I did, 20. Okay, right? Now, instead of, notice it's the same thing for the numerator here, right? In the second part of the calculation. So all I'm going to do is hit second entry, so I don't have to retype that numerator. And remember, my calculator overrides. So then I just type out my other chi-squared value, which was 10.283. And I got roughly now I have a confidence interval for my what? Standard deviation or variance right now? Variance, right? But it asks for the confidence interval of because that's what we really use, right? Like the variance is weird, right? So the variance is actually measured in points squared. I don't even know what the hell that is. How do you square an IQ point? Right? Like how do you multiply an IQ by another? I don't know. So how do we go from the standard deviation? How do we go from variance to standard deviation? So we're just going to take the square root. Now, again, there's a trick on your calculator so you don't have to, right? Like I could type this number in, but that wouldn't be that precise, right? You want to, it's best to square, to not, you don't want to, unless you have to, it's best to not round in the middle of a problem, correct? So let me show you again a trick that we can use for that. So I'm going to do second, and then notice this sign right here is squared, so I'm going to do square root, and then hit second, answer. So that got us the square, so I'd write that down. That's the square root of the bigger number, so that's the one on the right. Now it might seem like I have to type out the one on the left again, but I actually don't because I can hit second entry, then I get answer, square root answer again. I don't want that. Second entry again. Don't want that, right? Because that's divided by the 10, right? Second entry again. Now I have that first number. Now it appeared again, correct? Then I can do second, square root, second, answer. $10.99. Oh, you 11.0. You not mean 11.1. You meant 11.0, correct? Yes. So let's round that up. Let's say that's 11.0. I mean, technically, I should have the same number of decimal places as I do here, but that's just too many, right? So I'm 95% confident that my standard deviation is between 11.0 and 20.4. Now, hopefully remember this. We always seem to forget this word. What is my point estimator of for the population standard deviation? It's simply it's just the corresponding number. The point estimator is easy. The point estimator for example, the point estimator for population mean was sample mean, because that's the way you would guess. So the point estimator, right? So this is a range, but if you had to guess what's the sample standard, the population standard deviation, you had to guess a single number, you would guess 2.9, right? Yes, so notice that is the number you would guess, right? And before, right, the number that you would, because it was a symmetric distribution, right? In our warm-up, that's my point. I'm going to just demonstrate that, right? And here, it was exact, like our point estimator was exactly in the middle of our confidence interval. You cannot, so in between, so notice our point estimator is 14.3. Is 14.3 dead in the center of 11 and 20? Well, this is roughly a distance of 3 something, right? And this is a distance of 6. Do we see that? (14.3) is not in the center here, which is why we have a special formula. Questions? Before we found the margin of error, right? And we add for the mean, right? We added it and we subtracted it, which meant our point estimator was dead in the center, which made sense because every distribution we used until now had what property? They were all they were in the middle because what's true about the distribution? Well, one of them was normal, one of them was the student's t distribution. Yes, they were both symmetric, right? It was exactly in the middle because they were symmetric. This one is not symmetric, it's skewed, so you wouldn't expect it. Yeah, symmetrical here, right? Which is why there's there's 2 formulas instead of just 1, right? Hopefully we're starting to see that pattern. Now, before, right, we did briefly, I gave you a formula for calculating sample size, right? Do you remember this? So I said, if I want you to be within, I want you to get a sample. We're going to conduct a study, and I want it to estimate my mean within 1 inch, right? I told you how to calculate a sample size large enough to do that. Now, since this is more complicated, calculating the needed sample size will be more complicated. So, in fact, it's so complicated and complex, guess what? You're going to be happy about what I'm going to say. What? It's too complicated, right? And it's not as important because we're not as interested in usually estimating standard deviation. So ahead of time. So, but you do need to be able to know how to do this, right? This is just another problem. So why don't you try this in the next 5 minutes? Then I will go over it, right? And you already know the formula to use.
Wait.
I'm not going to tell you, I need my standard deviation to be within 1/10 of a gram. How big does my sample size need to be? Right? You're going to be given n and calculate the confidence interval. You're not going to have to do the opposite. So just follow the same procedure. Sure, you would like to know how you did on your celebrations? I can't tell you because someone has not taken it yet. I really don't know where the heck everyone is today, but that's their problem, I guess. I'm sure they'll all watch the video. So all you have to do is pull out the information. The only thing that's a little bit tricky is calculating, was determining the chi-squared L and chi-squared R, right? Anything else? Just the formula. No. So read it more carefully. So this is currently, so they changed the procedure, right? Right, so they did a new procedure, and this is the sample. Okay, this is the standard deviation you're going to use. So this standard deviation, the one that's mentioned there, that is the, so it says currently being minted, right? They're going to try to do, they're doing a new procedure, right? So if you think about it, you want every quarter to be ideally the same. Now they won't be the same, which is hence the standard deviation in weight. They're trying a new procedure, but they only were able to do it with 24 quarters. Now, it seems that the standard deviation is lower, right? But this is a sample standard deviation, right? We want to get a confidence interval around that sample standard deviation to see if it really is lower. You see what I'm saying? I might go a minute or two over because I want to spend time going over this, right? Because it'll be good if you figure this out. Okay, just because we have time, not much time left, I want to go over this problem. Let's go through it. Okay, so that's the formula you use. Then we just need to figure out what's what. Okay, so N here, everybody, is 24. And S is 0.049. If that was confusing, you can just notice that was the only one that was a sample one, right? A change was done, right? And we want to see, is the standard deviation lower after the change, right? Or is it just, hey, the first 24 happened to be well by chance, right? So we want to get a confidence interval. And what else do we need, Bobby, to calculate this? What's missing? Chi. I know it seems like it should be chi. I gotcha. It's spelled like that too. No one, lucky there will be no oral exam for this class. So, all right. Now, what is the confidence level, Bobby? 95. Okay. And the degrees of freedom is 23. So don't pack up until we finish. Trust me, you want to make sure that you were doing this right. Okay, so we now look at the table. Chi-squared table, right? Okay. And we have, what was it, 23 degrees of freedom, did I say? Okay, and we have 95% in the middle. So I think it's easiest to find, so if 95% is in the middle, Bobby, what percent is in the right wing? Okay, so I look at the last column, second to last, third to last, fourth to last. Third to last. Right, 0.25. You even said that. But do I use the 95 one at all, Bobby? Go ahead, you got it.
The XL, right?
Yes. Right, Bob, because the 95 one would have 5% to the left, right? And that we have 95% in the middle, so it's distributed, cut in half, right? So, Bobby, if you get stuck with that, can you get this one? Yeah, then you just subtract that one from one, and that'll get you the other one. Both ways will get you the same. Okay, so these are our values then. Okay, so that's x squared r, L, and x squared r, okay? Just okay. So then let me just finish this, right? X squared L is 10 point. Okay. Oh, okay. But everything else, hopefully you did. So then it's 23. Then you can put the whole thing in the square root if you want, right? So I'm going to do it like this. Right, well, now let me write it. So it won't let me write there.
Oh, yeah, it's 11.
11 point, what did I write? Oh. And I didn't do it. What was it, 11 point? Actually, I wrote that down. Wrote it down. Oh, I didn't do that wrong. I was looking at the notes for the previous slide. I don't know if that's better or worse. Probably worse, right? So that would give me variance. You take the square root of each of these to get your standard deviation. There's a square root there. And then I get 0.039. Then let's try to interpret this. Bob, you can at least, if you got stuck there, you can help me interpret this, right? So what was the old standard deviation? So yeah, so that was the old process. And the whole point of doing the new process is we saw this new process will do what to the standard deviation? Nope. Okay.
That's not even.
Not really a thing. Okay, Bobby, if I'm making a machine that makes quarters, what do you want all the quarters to be? Yes. So what is good, a high standard deviation or a low standard deviation? So the whole point of implementing the new process was lower standard deviation. Now, we did with our sample, but at 95% confidence interval, we're from here, 0.039 to 0.69. What do you notice about our original standard deviation with relationship to this interval? Well, isn't it inside? Is this original standard deviation inside of our confidence interval?
Yes.
So is there a possibility that our new standard deviation is above 0.062? So are we confident that this thing lowered the standard deviation? No, it seems it's towards the far right end of our interval, right? So if you said you have to guess, right, your life depends on it, I would say yes. But am I confident of that answer? No, right? So the answer is, does it appear to be effective? The answer is maybe. Like, I would say you can't be confident of it because the old standard deviation right? We'd be confident if this old standard deviation was totally out, was to the right of this confidence interval, right? But it's inside there. So now it's definitely towards the right end of it, so probably lower, but right, like you could easily, like if you're the person who came up with this process, you're going to want to do more testing, or you're going to want to refine this process before you report it, because you don't want to sell a whole, you want to say, boss, at the Mint, right? If you reconfigure all your, spend all month reconfiguring all your machines, this probably will decrease the standard deviation. You see what I'm saying, right? By the way, has anyone ever seen them make the coins? I went to Philadelphia. You can, at the Mint, they have a walkway over the top. You go, you choose, you call them, find them when the tours are. You can actually see them make all the coins. I've done that many times.